My name is Kirk Townsend. My official title is an engineering geologist with the California Geological Survey. My kind of working title, though, is a landslide hazards geologist. And I work with the Regional Geologic and Landslides Mapping Program at the California Geological Survey, which is nested within Department of Conservation within the state government system. I attended Cal Poly in San Luis Obispo, California for my undergrad. Started out as a declared civil engineering major and made it 1 or 2 quarters in before I bailed from the program. And what was really helpful, at least for making the decision initially to leave engineering, is Cal Poly, give them credit, they organized their major so that one of your very first term at the school, you take an introduction to the major that you've declared, and it's very informal. It's essentially just an opportunity to talk with some professionals. So they bring in a guest lecturer every week, and it's just some working professional working in some aspect, with the same degree, having earned the same degree that you're pursuing in that major. And week after week, I was like, that doesn't really sound that appealing to me. I'm not really that interested in that. And it got towards the end of the term, and I still didn't really have anything within the civil engineering program that kind of spoke to me or something that like I could see myself doing into the future. But growing up, I always did kind of have a bit of a geoscience interest, but it was just kind of I guess I would call it tangential growing up. It's like I grew up just outside of Yosemite National Park, and like the glacial history of the park and the composition of the rocks and the things that I was seeing on the ground, it was always interesting to me. But it was an interest that people recognized around me, but never really suggested as a possible career direction or a direction to pursue, because at least in my family or close network growing up, no one knew what the applications of those interests were. So I started taking a few additional introductory classes, just like they're 1 or 2 credits each my first year at Cal Poly. And I took the one for geosciences, and they introduced us to a handful of people who were working in different fields. I think one person was like an environmental geoscientist working for a county, and then another came from an oil and gas background. And just having exposure to a couple working professionals is like, well, I think geoscience is maybe something that you can actually pursue a career in. It isn't just kind of nerding out over rocks. Like, there are people who value the nerding out over rocks. They're willing to employ you to do that in a certain capacity. So it was in my first year at Cal Poly that I transitioned to a geosciences major. And so that was all well and good. I was starting to think about where I might go with that education as I was getting closer to my junior and senior year. And one of the critical pieces of advice that I got from faculty members at the time was to pursue some sort of internship or some sort of applied experience. It's great to have a degree. A degree prepares you for some of the work that you might be pursuing in the future, but it's really the like extracurricular exposure and activities that will differentiate you from maybe other students, because everyone in your program is essentially going to be taking the same coursework. So how do you differentiate yourself from someone who's taking the same suite of classes as you? So I started talking with my faculty at the institution to try and get an idea of like who hires interns, where can I go as an intern? And the program that kept getting recommended to me was the GeoCorps America program. And I'll be honest that I don't really know what the current status of that program is today. So hopefully it's not bad advice to say like, students, go out and see what it looks like. At the time, this was 15 years ago now, maybe. It was a really big program. So they had maybe 30, 40, 50, something like that positions that were offered nationwide. And it was an opportunity to take generally a student, someone who's either working towards their undergraduate degree or graduate degree, and place them into an applied position at a federal agency, whether that be National Park Service or Forest Service or the BLM. So I applied for several of those positions and then eventually landed one with the Sierra National Forest as a soil scientist. So this is where maybe leveraging some of your like unique aspects of coursework becomes really important, because getting into that position, I essentially just had coursework, right? I didn't really have a whole lot of other unique experiences yet, in order to kind of differentiate myself amongst the pool of candidates for that position. But I did have 4 or 5 soils classes, which most geology, geomorphology programs aren't going to have that kind of breadth of soil specific classes. So that was what I leaned into. And that was one of the reasons why I applied to that position specifically, is because I recognized what was unique about my educational background at that time, and then tried to use that to differentiate myself from other folks who might be applying for similar positions. That's kind of what got me into that internship. But then having that internship experience was immensely valuable for me moving forward. So that ended up being the really important experience, that kind of helped differentiate me from other candidates going into grad school. So initially it was Utah State University. I applied for the master's degree program there. That's where I met Natalie, and ended up getting in with a fellowship that funded me for a couple of years. And that was research focused. I was working on desert fluvial systems and trying to understand what caused them to either aggrade, fill up with sediment, or in size over time. And it was a really interesting project, but I wasn't sure if that was the field that I really wanted to pursue going forward. So I applied for a master's degree, was talked into maybe looking into a PhD, and then decided, you know what, I think, I'm going to take the master's degree here. So I'm not sure if that's exactly the field that I want to pursue. And I'm also not sure what kind of careers I was interested in at the time. But near the end of that, I took a course, Tectonic Geomorphology, taught by Joel Pedersen.
My advisor.
Yeah, Natalie's advisor. And that was the like, whoa, this is cool. Like there's cool stuff in geomorphology. And I, despite maybe not being as interested in the research I was pursuing in my master's degree as I would have liked to have been, I did enjoy the research process a lot. So that was taking that coursework was the realization, or was what led me to recognize that, there are these research interests that I could pursue, and that I could see myself, spending 5+ years working on. So it was after taking that course that I decided, you know what, I don't really like the lay of the land of positions, that I am eligible for with a master's degree. I wanted to do something that required more creativity and a bit more research chops than what I thought I was eligible for at the time. So I decided to apply for PhD programs, which is what eventually led me to the University of Michigan. So started at the University of Michigan as a PhD student in 2016, I believe. And most of my research projects were focused in Southern California and the South Island of New Zealand. So they're tectonically active places, that are also geologically very young. And the focus of my dissertation kind of pivoted into this focus on landscape evolution, but from kind of a engineering, geology, geotechnical engineering perspective, on rock strength. How do we measure the strength of rock masses? What scale of measurement is relevant to geomorphic processes? And once we figure out, one, how to measure the rock strength, the scale dependency of the strength that we're measuring, how do those sets of data influence the evolution of the landscape at like a mountain belt scale? So it was a really kind of nicely balanced dissertation, in the sense that I got to develop some really practical skills and become familiar with a lot of the applied geotechnical engineering literature, while also using that to leverage some very kind of high level academic questions that maybe didn't necessarily have a direct implication for, society at large, or engineering geology per se. It was the development of the skills along the way that became really important. It's what kind of set me up for, pivoting into an applied geoscience role following my PhD. And the one thing that I would add too is near the end of my dissertation work, I unfortunately or fortunately, depending on how you look at it now, my field area burned in a series of wildfires. First, it was the Thomas wildfire, 2018, and then later that same year, the Woolsey fire in the Santa Monica Mountains. And these were regions that I had already developed some pretty large, both geotechnical and thermochronology databases for. And I had an idea at the time, which was how does rock strength contribute to post-wildfire erosion? Now that we've assembled these databases of, landscape scale strength, can we learn something about the influence of rock mass mechanical properties or regolith properties and the distribution of erosion following a wildfire? So that question essentially became the starting point that I used to reach out to some folks at the USGS who had been on the ground after the Woolsey fire specifically, to do their initial post-wildfire assessments towards understanding what the debris flow hazard was going to be in the following winter season. And those initial connections turned into a couple meetings, including an in-person meeting at the AGU conference I think it was in Washington, D.C. that year. And that eventually led to a collaboration, including NSF funding, that I was able to use to go to the Hazard Science Center in Golden, Colorado for 4 months near the tail end of my dissertation to kind of work on this question and work with those folks. And that experience was also immensely valuable for just one, adding to my kind of applied engineering geology skill sets, and then also making a lot of connections with people who are very prominent in that field. Those are names that folks in the applied geoscience community, consulting firms, state government, they all recognize those names. So having those people as collaborators and having those people available to write letters of recommendation or just pick up a phone and kind of vouch for you is really, really important, really helpful.
Did you kind of like create yourself a bonus job at the end of your PhD? Is that what I'm hearing?
Kind of, yeah. So I was still technically on paper a PhD student at the University of Michigan, but the funding was from the National Science Foundation, but it was I think they called it the intern program, which is a acronym for something. It's all capital, interns capitalized. But it's a program that the NSF runs that allows graduate students to pursue an applied research internship outside of their institution. So it can be either government, state or federal, or it can be with a private company, a consulting firm, oil and gas. It doesn't really matter, just as long as it's an applied research project. And it's competitive to some extent. So like you have to write a proposal that then goes to the NSF for review. But my understanding is that they're pretty flexible and open to ideas. After finishing my PhD, I went on to this consulting firm called Exponent. And Exponent itself is a really large applied scientific and engineering consulting firm. They have automotive scientists and chemists, people in the medical field. So just kind of a large umbrella over science and engineering generally. I joined the civil engineering group at Exponent, which is mostly geotechnical engineers and engineering geologists. And the reason why I was hired, I actually never applied for a position. I was found and recruited by Exponent, by the senior scientists within the group, was for my post-wildfire research that I pursued at the end of my dissertation with the USGS. So there's specifically here in Southern California, post-wildfire erosion, debris flows, hazards generally is an ongoing issue for the region. So the hazards from a wildfire persist for years after the fire actually burns, right? The hill slopes are stripped of vegetation, the hydrophobic properties of the soils change, and erosion and debris flow hazards will persist for years after the fact. And there remains, as a result of this continuing hazard, there's a continuing impact to residences and a question, multiple years after a fire, as to whether or not the wildfire was responsible for some of the damages that a homeowner, for example, might face on a property. So I was doing a lot of insurance claim investigations. That was largely the reason why I was brought into this role. So if you're a, let's just say as a hypothetical, if you're a homeowner and you live kind of at the urban wildland interface, and your home experiences damage due to a landslide or debris flow, the first thing you're going to do is file a claim with your insurance company. But most homeowner insurance policies have exclusions for earth movement and they have exclusions for flood. So generally, if it's just the hill slope failed in a landslide, you're unlikely to get coverage for that if you're the homeowner. But most homeowner insurance policies have coverage for wildfire, and that includes the cascading impacts of wildfire years after the fact. So if the landslide that impacted your home was instead only possible because that same hill slope burned 1, 2, 5 years before that landslide occurred, then you're going to get coverage for that event. The problem with consulting and maybe the model that Exponent works with generally is that a lot of the projects are kind of turn and burn. Like the timelines are really short, the budgets are pretty limited, so you don't really have time to kind of get into the weeds. And coming from an academic background, doing research both in my master's and PhD, I really liked the sustained drive over time and having the timelines that let me really get deep into the weeds on whatever problems I was exploring. So I started to feel like a lot of the analyses that I was doing were a bit superficial in the sense that, with a $5,000 budget and maybe 30 hours, there's only so much analyses that I can do. And at the end of that, I have to issue an opinion on what happened or what I think contributed to, the event that I was there to document. But I often just felt like that opinion, like there were additional analyses and different things that I would want to do before forming that opinion, but there just wasn't time and budget to do that. So state governments and state geological surveys kind of nicely fit the bill for me. So there's still applied agencies. They're not like the USGS, the federal version, which is really research focused. Their scientists are mostly engaged in, the peer-reviewed literature and running studies that eventually turn into publications. So the State Geological Survey has more responsibilities for developing applied products that actually go to serve the public interest in a more direct and tangible way. But the timelines for project development are long enough where you can really figure out or dive deep into a subject. And the problems that these state geological surveys often face do require the same kind of research chops that you might have at a USGS. It's just the final product is going to be something that goes out to the public, like a hazard assessment or a susceptibility map, rather than a peer-reviewed article. But in the process of doing that, there is opportunity to actually develop peer-reviewed science as well. There's, in consulting, there's always a client, right? And everyone at the consulting company that I worked for had a PhD. They're trained scientists. Most people had some peer-reviewed publications that they had developed along the way prior to joining the company. So, everyone follows the scientific method. You let the science speak first. That all being said, you are in some, capacity an advocate for your client. So that doesn't mean that you're fabricating things. It doesn't mean that you're excluding information. You're still following the science, but you're letting your client know when they're in the wrong, and you're helping them develop reasonable accommodations if they are in the wrong. So one example that I would use is I had a project with a city here in Southern California. The client was the city itself, and the city was being sued by a business owner who was alleging that construction of a new water retention basin, floodwater retention basin, upslope of his property, by the city, was causing water intrusion onto his property. So we were hired by the city, to be their expert witness and to run an investigation into the causes of the water intrusion on that property. And essentially halfway through the investigation, we went to our client and said, yeah, this issue would not have happened were it not for the construction of your water retention basin. Like, you own this, this is your responsibility. So instead of basically telling the city that information and then the city trying to fight it, what the investigation pivoted to was, okay, what's in a reasonable repair for this situation? How much realistically should you be on the hook for, dollars and cents to repair the issue and make the business owner whole? And that was still a really valuable exercise because, despite the city being in the wrong from a, mechanics perspective, what actually happened, the attorneys for the business owner were asking for several $1,000,000 to conduct the repair when the same repair could be done for a couple $100,000. Like an order of magnitude difference in the cost, right? So, this all goes to say we're following the scientific method, but you are in some capacity an advocate for your client and you're helping them make, the best informed decision that they can make. So it's really, important to hold yourself up to your own standards and, scientific rigor. But that doesn't mean that you are not going to run into bad faith arguments and bad science in that role. And it kind of sometimes just feels like, whack-a-mole, where, you're reading the opposing side's expert report and finding all of these really bad issues. So you issue a rebuttal report that goes after all of the issues. And then they come back with their own rebuttal report that has a whole new set of fallacies and issues and cherry picking data. So it can get a little exhausting to kind of have to, fight that. And I don't want to like say what percentages were in terms of, how many cases I worked on were opposite bad actors or not, but it was a substantial number. So it's out there.
Yeah.
And the sad and scary part about it is, these are the experts in litigation, right? So, one set of experts can clearly identify major fallacies and errors in another expert's set of work, but to a jury or the attorneys or the judge, they don't have the educational and, applied background to really understand who's right. They just see two experts disagreeing with each other. I guess kind of going back to one of the unfortunate things probably about consulting is that it's always entirely dependent on the budget and the amount of time that the client is willing to allow you to spend. So you have to scale your investigations to the budget and the time. Usually we'd end up working with attorneys and clients that we already had a background with. So you could help the client kind of shape what you think, an appropriate investigation would be and, what the timeline and budget for that investigation should end up looking like. And if they're, a law firm with, any hope of winning, they're going to kind of listen to you and, and work with you there. But, that wasn't always the case. So for a lot of these insurance claim investigations, these are pretty quick. They're maybe in the order of just a few weeks because the homeowner is waiting on you as the engineering expert or the geoscience expert to issue your report before the insurance company is going to make a coverage decision. So all the time that you take, whatever time that ends up being, is just delaying any action on a homeowner's property that is obviously damaged. It's the whole reason you went out there. So those might be a handful of weeks. The budget might be, in the $5,000 to $10,000 range, which maybe is 40 hours of work or so, so basically a week's worth of hours, essentially. So for those, the investigation would be a site visit. So actually going out to the residence, interviewing the homeowner to get their take on what happened and when it happened, and then documenting the damage, and then walking around either the channels or the hill slopes, looking for the origin of the landslide or the debris. From there, going back into the office, then it's a handful of kind of standard evaluations and analyses we do, including like a precipitation analysis, looking for when did it rain, how much did it rain, what was the intensity of the rain, how does it relate to the homeowner's statement of the timing. And then from there, we might do a quick LiDAR analysis if the data is available. So we'll take a look, generate some slope models, a DEM. If we have multiple generations of LiDAR data, LiDAR data that was flown at 2 different times over the same spot, do a difference analysis on that to see how that landscape has changed over time, and if change is a constant or if it's relatively stable over time. And then the last piece is the fire history. So understanding when the landscape burned, what the intensity of the burn was, and if there were any sort of land movement consequences of that burn shortly after the fire happened. And then that all goes into a report that might be something like 15 pages long that then gets issued to the client. These were always a little tricky though, because it's an important question for a coverage decision for the homeowner and for the insurance company. But that question, we're 5 years out from a wildfire and we've had a landslide. Is that landslide related to the fire? That is like active research within both the academic and the applied geoscience research community. Francis Rangers, who was the person at the USGS who I worked with for my internship, he's published a couple papers in 2020 and 2021 that are, really the only peer-reviewed documentation that in this role I could point to for these assessments. And it is ongoing research, and it is partially opportunistic in that you have to have the events happen in order to do the science. You have to have a landscape burn, and then you need to have rain of varying intensities hit that landscape several years after a fire. And then you have to have the resources to go out and then map and document what happened. So you have to kind of have all of the pieces aligned to do that research. And the client doesn't really care about that. They just want to know whether or not the landslide was caused by the fire 5 years before. So explaining the state of the applied geoscience and research community and their take on that is not what they're interested in. So this is where you're issuing your opinion on what happened, and you're still stamping it with your professional geologist or professional engineering license, but recognizing what the limitations are, both in terms of the status of the science as well as your own budget considerations. And putting that into the report could be really important. So that was like, the short time and short budget side of the work. When people start suing each other, when there's litigation involved, everything ratchets it up. So take this same scenario of a homeowner who has a landslide impact their property 5 years after a fire. Let's say that the insurance company, after seeing our report, denies coverage, and the homeowner doesn't like that, so they go to sue the insurance company to force them to provide coverage. Then things start to change, and experts are hired on both sides of that lawsuit, both by the insurance company as well as by the homeowner. And the budgets are going to increase, and there's going to be a lot more time and energy developed or allotted to explore the issue further. Yeah, so a lot of those skills have kind of carried over, but the timelines are very different and the deliverables are very different. And it's also just on the whole a much less combative environment, because we're not on either side of a court case. No one's suing each other over something, so it's like you just kind of like take the temperature down a little bit to start with. But the experiences that I get in consulting, which is a lot of the softer skills that you just described. How do you find information? Where do you go to get that information? Is this an analysis that you're unfamiliar with? Like, take a look at the literature and figure out how to do it. A lot of those skills are not skills that I necessarily gained in grad school, but really are kind of came into being during my time in consulting. And it really develops, having this skill set creates a much more, trying to figure out how I want to say it. become a much more adaptable scientist and a much more adaptable geologist through developing these skill sets. And that adaptability is one of the things that the Geological Survey was interested in. One of the reasons that I was ended up getting into this role. So I spent a lot of time both at the end of my dissertation and at consulting focused on post-wildfire hazards, and specifically this like longer timeline of landslides in burn areas, 2 to 5 years or even 10 years after a wildfire. It's a really new area of research. And it's the exposure to that science, the interest in that science, and the familiarity with the literature that I gained mostly through these insurance claim investigations that ended up being really critical into coming into this role. The day to day, I'm still kind of figuring that out because I'm only 8 weeks into the role. But the tropical storm response was kind of illustrative of how things would be a little bit different. So I started in mid-August with the State Geological Survey, and 1 week into my job, the first tropical storm to hit California in a century rolls up into the LA basin. So that event, everyone, the forecasting was really good. People kind of saw what was coming. We had time to prepare for it. So the state government up and down the spectrum, all the way from the governor's office down to us, was mobilized into this response center where everyone was sharing information. This was some office in the Sacramento area. And that information was being distributed down the chain to people like me, who were the field response team. So I was part of a group of three, who essentially tasked with documenting what was happening and understanding what was happening, where it was happening, in terms of mostly debris flows and landsliding. And the goals for this one were just to get a sense of where and what was happening to then distribute to other people within the state government, groups like Caltrans, for example, the highway agency that's going to have to respond to any event that might impact the highway. But then there was also, we need to know as a scientific agency what causes landslides to happen and debris flows to happen, and specifically, what precipitation histories, both in terms of quantity of antecedent precipitation, so the accumulated precipitation over time, as well as the intensity of precipitation, how much is falling per hour, for example. We need to do a better job of understanding what the landscape response would be to those different types of precipitation. So anytime an event happens, a landslide or debris flow happens, if we have good precipitation data, that creates another data point that we can use in future efforts to improve our modeling of the triggers for landsliding. So years down the, I don't want to say years, but one of the future goals and the reason that I was hired into this position is that we want to improve our modeling of precipitation-induced landsliding, specifically related to climate change. We expect that California specifically is going to go through these more extreme cycles. So there might be a prolonged drought that lasts for a few years, which will be followed by an extremely wet year, right? So those two end members are going to have very different hill slope and landsliding responses when rainfall hits. And we want to get a better understanding of what the hazards are facing these communities on the urban wildland interface with climate change and specifically precipitation-induced landsliding. So to develop these models, you have to have real-world data. A model just lives in a vacuum unless you actually have real data to test it against. So these type of events become the data that can then go into those future modeling efforts. So there these two applications in real time that we're thinking about as we're documenting these events. There's other people within the state government that need to be aware of what's happened at a specific location. And then longer term, this is the data that we're going to use to better understand the hazards facing the state. We understand that earthquakes drive lots of landsliding. So the 1994 Northridge earthquake it struck Southern California, produced something like 11,000 landslides within a relatively small geographic footprint. Then you have events like the Gorka earthquake, which hit Nepal in 2015. Something like 30,000 landslides were mapped after that event. The Wenchuan earthquake in China in 2008, that was something like, I think it was like 100,000 landslides that were ultimately mapped following that event. So earthquakes are one of the biggest drivers of landsliding that we see, and one of the biggest drivers of landscape evolution over really long time scales. So obviously those are huge hazards that a federal or state geological survey wants to understand. So the California Geological Survey has a seismic hazards program. It's a separate program from what I'm in, but one of the spaces that that program is focused on is the hill slope response following an earthquake. So they're also looking at liquefaction potential, shaking, but they have a dedicated staff member who's focused on co-seismic landsliding. And a really important part to forecasting what the hill slope response might be following an earthquake is an understanding of what the past landsliding has looked in that space. So some of the products that I'm working on developing are just landslide inventories. So these are essentially maps showing the location of known landslides, whether they were witnessed directly or if we're able to infer their presence based off of the morphology of the landscape as it exists today. And these landslide inventories are essentially locations in a modeling sense of zero strength. So, some of the important factors that a geologist modeling landslides during an earthquake is going to be focused on are the topography, how steep is the landscape. It's going to be the intensity of the shaking, which you can simulate based off of the geometry of a fault, prior to an earthquake. And then it's the strength of the rocks and the soil that underlies the hill slopes. So one of the assumptions that we can make from the rock strength side of things is that if a landslide has already happened in a location, then that is a region of zero strength, right? Essentially, in an engineering geology sense, the factor of safety for failure is already one or less. This has already failed. It's already exceeded the resistance to failure that is imparted or is a consequence of the strength of the material. So this is an area of zero strength. So that data then gets fed into the seismic hazard assessments as, this is a location of zero rock strength. It has already failed. Therefore, when we start shaking it, this is a location that is likely to fail again in a future earthquake. Some of the skills that I really wish I had developed more prior to joining either the consulting world and the now state government is coding on open source platforms. So I, as a university, student and graduate student, had access to things like MATLAB, which is a really valuable resource, and it's kind of a a nice friendly way to get into coding. But it is a GUI interface that is a little bit more user friendly and intuitive than just like coding in Linux, for example. But it also costs a lot of money. And the thing that you learn getting out of academia is that wherever a private company can shed costs, they're going to do it. So, if you can remove something like MATLAB, they're not going to fund it, and they're going to ask you to look for other potential platforms. So I wish I had spent a bit more time exploring open source platforms. The nice thing moving into the State Geological Survey is that there's, I kind of going back to the longer timelines and greater degree of patience, is they're willing to let you spend a bit of time to develop those skill sets. There's other products that need to be developed along the way, but if there's a justifiable reason for you to invest the time into gaining the additional experience and knowledge, they're willing to let you do that. But that would be number one is just familiarize yourself with the open source equivalents of some of the platforms or software technology in general. that you're exposed to in grad school and spending a little bit of time with those open source equivalents. I think the other really important trait that I only recently recognized that I kind of developed was a flexibility and an adaptability to, respond to what was happening around me. So I never, starting out as an undergrad, I never really had a singular professional career goal in mind. I didn't know that like I wanted to be, an environmental consultant working for this company, or I wanted to be a petroleum geologist working for this company, or I wanted to be, a tenure track faculty member at this institution. I never had that at any points in my, academic and professional development. But I had interests. I had things that I was really, interested in pursuing, focused broadly around geomorphology and landscape evolution. And there's obvious applications of that kind of skill set, but I had never nailed down the specific career or application that I wanted to do because it was all generally pretty interesting to me. So one of the things that's really benefited me is being willing to respond to, outside things as they happen. So for example, this pivot near the end of my PhD towards the post wildfire erosion and the internship that I ended up doing with the USGS, that only happened because my field area burned in a wildfire. That wasn't planned. I'm not an arsonist. I didn't go out and set the fire hoping for an interesting project. It just happened. And for a couple of weeks, it really sucked because I was supposed to go out into the field as the fire was happening. So I had to cancel the plans. But, that led to these questions. And those questions ended up turning into this collaboration with the USGS and then an internship. And then that's kind of the experience that then got my foot into the door with the consulting company that I joined after graduate school. And reflecting back now, had I not been willing to like kind of just pivot a little bit and explore something different or new at the time, if I had just stayed on my narrow track of I'm working on this analysis right now for this paper that's going to be chapter 3 of my dissertation. If I had been on that rigid track, none of those experiences would have happened. And I likely wouldn't be in the role that I'm in today.